We did it. Okay. All right. God, the modern age when we show up when we are supposed to.
Oh my goodness.
Yeah, I know. It's crazy. Do you remember the days of yore when we could be up to 15 minutes late?
I do remember the days
because of us and technology.
I was much younger then.
Oh, so much.
I got
so much
very
the technology sometimes.
Yeah, mostly the technology.
Google Hangouts has decided it won't like anybody today, so
yes.
Yeah. Yeah, no, it's very weird that we show up pretty much precisely at the start time. It's bracing.
How we've grown.
How we've grown, yeah. How we've become, professional, fulfilling our commitment.
Let's not go that far.
Yeah, all right. How we become acceptable.
There you go.
Yeah.
Industry standard.
Yeah. All right.
Good enough for government work.
I'm not really centered on my box, am I? Not really.
Find today's.
See, I'm futzing with mine too.
I'm just gonna move my computer. I got it, Pam.
Yeah, I love how Kimberly and I are like, no, I gotta fix I gotta be centered. I can't not.
It would bug me. It would be one of those things that would bug me. The whole show.
This wasn't a coincidence.
This is technically green. It's sort of a lightish green. It's not white. It looks white.
I think Alexander just has that effect going. for him down there.
Now Alexander looks all professional with the whiteboard.
That's true. Yeah.
I have
yeah.
one of those.
I don't ever
Meanwhile,
hardly
I just
use
have-
that, to be honest.
Like
I just have bookshelf of chaos.
yeah.
Which also looks
I've
very
often
professional.
complained about my piece of paper running out of battery during class. It's super annoying doing all of my notes digitally.
Yeah, what you can't see, you wouldn't want to see where I am in the back room in the trailer, surrounded
Still in
by
the trailer, right?
yeah. We're like, I keep saying we're a month away, and at this point, we're probably feels like we're 3 weeks away now. But
Ooh, now
but
you've fixed it.
we're running out of things to do to get done. But some of the big pieces.
Your
are still
virtual
waiting.
background is doing some heavy lifting right now.
That's exactly it. Yeah. I've sort of done the math. I think I've done like 100 shows in this tiny little trailer. Yeah, this tiny
what a
little
workhorse of a trailer.
more than that, probably. Yeah. Yeah. Sitting on a camp chair that's starting to tear itself apart. So yeah, on a bunch of pillows and some towels to keep me high enough, with my computer and gear all stuffed into a bed. Yeah,
That's a miracle of the modern era.
It really is a professional. You can't even tell.
Yeah.
It looks like I'm in space.
You're
well
pulling back the
lit.
curtain in a scary way.
Yeah, exactly.
Well, you are in space.
I know. That is how pro this studio is. Really, it's the cameras doing the heavy lifting. That's the part that I'm really grateful for. Is a really nice camera. All right, well, let's get started. I tire of our not doing a show. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, May 18th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about a lot of sad spacecraft. Voyager 1 glitch, leaky helmets, InSight powering down, and the possibility that Ceres moved quite a ways into the inner solar system. Joining me this week, we've got Beth Johnson. Hey, Beth.
Hello, Fraser.
How's it going?
Pretty good. Still renovating my house. The process continues.
Well, is that like the books? Is that hiding the renovation?
No, this room is basically the sacrosanct really haven't touched it room. When everything else is done, the chaos will encroach. Right now, this is like, please leave me alone.
Know what's happening when those books are starting to disappear and shift away. All right.
Yep.
We got Dr. Kimberly Cartier. Kimberly.
Hello, Fraser. Happy podcast day.
Happy podcast day to you too.
Happy podcast day.
How did you celebrate podcast day? Did you have your family with you together? And
I had my cat try and knock over my computer that's precariously perched right here. That's always an exciting event.
Consume the traditional happy podcast day feast.
Rice Krispie treats.
Nice. All right. And back from hiatus, we got Ashley Walker. Hey, Ashley, welcome back.
Hey, Fraser. How are you?
Good. Well, you know how I'm doing. Stuck in a trailer still, but almost out. What's news? Have you got some new research to tell us about? Anything new happening with your various mini projects?
Absolutely. So now I'm working on Neptune and Uranus, and I want to understand their atmospheres a little bit more. And also, Black and Astro Week is coming up next month.
What's happening for next month?
So we have a variety of events, and we're also introducing space law and policy. And we're also, in addition to space law and policy, we're also introducing space economics and space entrepreneurship.
Right on. And what's the best way for people to, I mean, we can talk about this later on in the show, but if people want to get involved in that, what's the best way to do that?
You can contact us at blackandastro.com.
Perfect. All right. Well, before we get on to this week's special guest, I want to give a huge shout out to our good friends of the Weekly Space Hangout crew. Our friends, our fans, our executive producers. You can join this amazing community. Go to wshcrew.space and they will give you all the information that you need to become really an executive producer of the show. All right, let's get on to the interview portion of the show. Joining us this week, we've got Alexander Madurowicz. Is that right? Did I get that right?
Pretty close.
Close.
Madurowicz.
Okay. Madurowicz. Thank you. So who are you? What do you do?
Well, hello, Fraser. It's great to be here. I am a physics PhD student at Stanford University. My research is all about direct imaging of extrasolar planets.
That is so cool. So where are we on the direct imaging of extrasolar planets right now? It's
been done.
It has been done.
For a small number of planets, they're very difficult to see. Turns out they're not very bright. And stars are much brighter. And they're very close by to those very bright stars. So it makes them really tough to see.
And give us a sense of the difference of brightness between the star and the planet.
Well, it depends on what kind of planet you want to look at. Right now,
kind of star, I guess.
And as the star as well. The planets that we've seen right now are mostly extremely massive, like Jupiter-sized or bigger planets that are also very young. And so the ratio of the brightness between these planets and their stars is like a factor of 1 million in brightness. The typical analogy I hear everybody always describe is it's like seeing a firefly next to a lighthouse. But
right.
I think that analogy doesn't actually really do justice to the extreme contrast ratio. So
and it's even more, right? For an Earth-sized planet next to a sun-like star, it's like many more orders of magnitude than that even.
Yeah, so the Earth is much smaller and less bright than like a Jupiter would be, and so that's more like 1 billion or 10 billion times the brightness.
And so what telescope do you think is gonna, of the telescopes that have actually been decided and are under construction or perhaps in space, just finishing off setting up their instruments, what's going to give us the best shot at actually seeing another planet, ideally like an Earth-sized world orbiting around a sun-like star?
Ooh, that's a tough one. So nobody's seen such a planet yet. So the first discovery of an Earth-like planet around a sun-like star has not happened. But I don't think that James Webb is really going to do direct imaging as well as do transit spectroscopy. So it'll be watching the star and the planet the planet cross in front of the star and the star dim a little bit. And Webb will do that one extremely well. Direct imaging is not exactly planned for space missions, but if you're familiar with the Roman Space Telescope, that has a plan to launch, I think, later this decade, and will use microlensing, and it'll be the first telescope that will detect large numbers of Earth-like planets around sun-like stars.
Of course, the downside with microlensing is you only get one shot at it, that you don't get to observe it. You get the one view and then it's gone.
Yeah. And it'll be good for making large statistical samples because you can do this on a lot of stars at the same time. But if you want to do detailed follow-up or characterization of specific planets, you're probably going to want dedicated instruments and probably using ground-based telescopes. You can build a lot bigger telescopes on the ground, and you need to have a really big telescope to get to the small angular separation you need to separate the planet and the starlight.
So let's talk about your sort of most recent work. You've been thinking about would be possible with a solar gravitational lens, and I'm sure a lot of the people that are watching this are familiar. I did an interview with Turyshev a couple of weeks ago about the solar gravitational lens. We went into tremendous detail about it. So for people who maybe aren't familiar, what is this idea of using the sun as a telescope?
Okay, so yeah, so you mentioned Turyshev. He's probably the world-leading expert in this idea. He has a multi-million-dollar NASA grant to investigate this concept. I'm just a student, playing around with my laptop and building simulations and testing things out. But I found a kind of interesting thing that they neglected to mention in their like 20 plus that he's published so far. And so that was sort of one of the big discoveries I shared recently. But the idea is that we would like to learn more about planets than what we currently know. And with any sensible sized telescope, one that you might conceivably build with your hands, a planet is so small and distant, it's just a speck of light. And if you really want to see the planet, like the way that we've seen pictures of Earth from space or other planets in the solar system from orbiters or other flyby missions, you either have to get really close to the planet with a modest-sized camera, or you need to have some enormous telescope. And so the genius, which was actually, I think, originally proposed by a Stanford professor von Eschelman in the 70s, is that you can use the gravitational lens of the sun like a giant primary lens in your telescope. And it's basically like a solar system-sized lens that you can exploit to make images of an unprecedented angular resolution and potentially even see the details on their surfaces and in their atmospheres.
And from what I understand, again, with my conversation with Dr. Churchev, using the sun as this gravitational lens is the equivalent of building a 90,000 kilometer sized telescope. Was his math on that? So that's
sure, yeah, that sounds about right.
That's tough. That's a big telescope.
That's like 10 times bigger than the Earth, or about something like that.
Yeah. That's a lot of material. That's a lot of work to build a telescope 90,000 kilometers across.
Yeah,
so
you might call that like a megastructure or something.
Yeah, exactly. So if you were to use this natural telescope lens, what level of resolution would that give you on an extrasolar planet?
Well, the answer is it depends on a lot of factors, actually, but you could conceivably resolve something like 10 or maybe 100 or perhaps even 1,000 pixels across an Earth-sized planet, depending on how many telescopes you want to deploy to its focal plane and how large they are, and which planet you're looking at. Is it close or nearby, like nearby or far away? So
now, like 1,000 total, would they give you 1,000 total pixels or 1,000 pixels across?
So I was thinking in just one axis. So 10 by 10 would be like a little postage stamp. 100 by 100 would be pretty high resolution, and 1,000 by 1,000, that's a megapixel image.
Yeah, megapixel resolution image of an extrasolar planet. Yes, please.
Yeah, I think everybody who knows anything about space and exoplanets wants to see a picture like this.
Yeah, that would be absolutely stunning. So, when I talk with Dr. Churchev, there's a lot about sort of.
I love how Kimberly and I are like, yes.
Yes,
please.
I want to see this.
Yeah.
Yes, please.
And so I guess, when I talked to Dr. Churchev, we talked about sort of sending the missions down that you would, you'd get out to say 550 astronomical units, and then you'd be able to start gathering this data, and you would just sort of fly down this pipeline, continuing to gather data on this one target that you've chosen. What is the wrinkle? What is the new research that you and your collaborator are adding to this idea?
Interesting. Okay, yes. So my collaborator is my advisor, Bruce McIntosh, who's also my source of funding. So I have to thank him for all the support he's given me and the freedom that he's given me to spend time exploring this very futuristic concept when I should be working on immediate, more pressing responsibilities.
No, absolutely not. This is the most important. Getting Kimberly a 1 megapixel image of an exosolar planet has got to be your highest priority.
Absolutely. You
Yeah.
can tell Dr. McIntosh that.
I'll take that. I'll keep that into consideration. But the wrinkle is related to the oblateness of the sun. So if you're familiar with that term oblateness, it's just that the sun is a little bit fatter around its waist than around the poles because it spins. It's in hydrostatic equilibrium, which just means that the pressures and the gravity balance. And if it wasn't spinning, it would be a perfect sphere or something close to it. But it's spinning, and it's spinning, so it's a little bit wider than it is tall. And this means that the lens of the sun has some unusual behavior. So if you're looking directly down at the pole, so you can, the rotation would just look like it's spinning around in your field of view. This fattening, this sort of goes away, and it sort of doesn't matter. And the lens behaves just like a point mass lens, which would be like the Schwarzschild solution, basically. But if instead you're sort of looking somewhere pointed along its equator, now all of a sudden this oblateness starts to matter, and it matters quite a bit. And it has a number of effects. One of them is that it makes the lens worse. It makes the magnification smaller. So one of the major advantages of the SGL is it has this enormous magnification. It's like a billion times in magnification. So a planet on the sky suddenly gets a billion times larger. That just makes it a billion times easier to measure. If you're looking along the equator, the magnification is a little less. It's like 10 million, not a billion. Bummer. It's still extremely helpful. But there's an advantage that comes with this disadvantage. And it's that the distribution of light that is in the Einstein ring has different properties. In particular, a point is re-imaged into this ring, this Einstein ring that forms around the sun, 4 times instead of 2. So when you have an ordinary point gravitational lens, like a spherically symmetric mass, you get 2 images, 2 points that form a sort of ring around, that form the Einstein ring. When you have this squashed lens, you get the Einstein cross, where there's 4 images. And these points move around the edge of the ring in a way that allows you to untangle the original images, which was sort of the big discovery in the paper. Although it's really not that surprising, because people studying lensing in like galaxies for, cosmological purposes are really familiar with, galaxy or clusters of galaxy lenses that behave very similarly.
Oh, so you get an Einstein cross because the galaxy isn't a nice sphere, or the big blob of dark matter out there that is containing the galaxy cluster isn't a perfect sphere. It's lumpy, and so you're getting this weird shapes around it.
Yeah, exactly. So there's some galaxy or galaxies, their mass distribution is not perfectly symmetric. It's maybe extended in one direction, and you get the formation of the 4 images, the Einstein cross.
Right.
And the same thing happens with the sun, but it's a lot more subtle because the sun is pretty close to being perfectly spherically symmetric.
And so you call this an advantage. So what does this give you?
One of the challenges with using a gravitational lens that's a point mass is that just by looking at this Einstein ring, you can't exactly tell what the planet is. You get some information, but it's not enough to give you the full image. When you have this oblate lens, that changes because of the mapping between the source coordinates and the ring coordinates is totally different. And there's not a specific kind of degeneracy. So there's a mapping that has an inverse. And so you can solve for this inverse, and you can recover the original image from just looking at the ring. Now this is pretty neat, but there were ideas to make full images of planets before the people were really aware of this oblateness. And so the trick they used is that you don't need to just keep the telescope in one spot. You can sort of scan the telescope around different locations, and by mixing up the alignment between the planet, the sun, and the craft, you can then sort of reconstruct the whole image of the planet. But this has its own problems because as you're moving around, the planet's rotating, the clouds are moving, it's changing. And so as you're moving around, you're getting snapshots at different points in time. And to combine those observations to make an honest reconstruction of the image is kind of complicated and it suffers from its own problems.
So
with this new idea, you can just take one picture, and with that one picture, invert the mapping and get the image.
So you could take the image with the Einstein cross and get the original image without having to like move the telescope around and try to fill in all the missing pieces.
Yes, that's the essence of the idea. Now, there are totally caveats with this, so I'd be happy to tell you all about the caveats.
Yeah,
the paper that I wrote was an extensive description of all of the caveats, and so yeah, take it with a grain of salt.
Right. Well, give me like your big caveat. What's the big bugbear on this one?
With the concept as a whole, or with this nuance about
with nuance? I mean, the concept of whole is how do you get a spacecraft out to 550 astronomical units that can last for 40 plus years with its own power before it can even start doing it. Like that's a big ask. But let's assume that all of that's been solved, and now you've got your spacecraft out there. Yeah. No. What are the and you're dealing with the flattened sphere that is the sun. What is the caveat that you're worried about with this solution to it?
Yeah, the most practical caveat to this particular method is the size of the telescope you send out there. So the things I said are true, like in theory, like if you had a telescope with sufficiently high resolution and sufficiently high signal to noise, there is a theoretical inverse of this mapping. But the practical limitation is that if you deploy an honest-sized telescope reasonably considered SNR, your measurements of the Einstein ring are far from perfect. They're contaminated by the corona. But not only that, the size of the telescope means that there's a blur intrinsic to your image. Your telescope forms a point spread function, the size of a point, depending on the diameter of the telescope. And this means that the information in the ring is smeared by your telescope's focal blur, basically.
Does a bigger telescope solve this problem?
Yeah, exactly. So if you have a bigger telescope, you have a tighter point spread function. You can resolve smaller details in the ring, so then you can conceivably get more out of the ring on its own. But with a regular sized telescope, you could probably only measure something like, 40 or so different locations independently around the ring. Yeah,
well, Khrushchev had said a 1 meter telescope was the size that he recommended, which is fairly reasonable. That's not a very big, too gigantic of a telescope.
Well, that's smaller than Hubble.
Yeah, way smaller than Hubble. Yeah, would do the trick. But would you want to go bigger? I mean, obviously, telescopes should always be bigger. I mean, that's a given. But
I think in the paper I was suggesting a Hubble size, so I think I used 2 meters, which it gives you a factor of 4 in collecting area. So that's not too shabby. But.
So what's the next step for your research?
In terms of this project, or in general?
Well, in terms of this project, are you just gonna, you're working on your PhD right now? Is this gonna form your dissertation, or are you just gonna move on and never think about solar gravitational lenses again?
Well, so this will be a chapter in my thesis, I think. I think there'll be 4 chapters. The other chapters will be other projects, probably more immediately relevant to exoplanet imaging at the present. I don't have any exact plans to continue my research on the solar gravitational lens in the future, but I think the possibility to do a postdoctoral project that extends this work is certainly there. I haven't made any decisions yet, though. I'm trying to finish the first 3. So.
It's the most exciting idea that is also kind of ludicrous. It sits in these 2 worlds for me. Yes, a megapixel image of an extrasolar planet that you could see like cities and forests and oceans and mountains and all that would be amazing. But at the same time, it's the level of long-term thinking is absolutely crazy. Well, it's absolutely fascinating work. What's the best way for people to keep track of the work that you're doing?
I don't have an answer to that question.
Archive,
I don't have any
guess.
public available channels or anything of that kind. So I'm sorry.
That's
someone
probably
wants to
best.
follow me, then maybe they can send me an email or something.
Yeah, Google Scholar. That's keep track of your papers and and watch your citation number go up. That's probably best. Yeah,
Sure.
yeah. Stay off Twitter. That's best.
I agree with you though. This idea is kind of at the border between lunacy and necessity. So,
yeah, that's perfect. That's exactly it. It is just so crazy. It's so crazy. It just might work. Oh, Alexander, it's been a pleasure to talk to you. Good luck. And if you do get the green light, let us know.
Well, thank you so much for having me.
All right, take care.
You're off air and can click away whenever you want.
Right, let's move on with the news portion of this week's episode. Ashley, let's talk about Voyager. What's going on?
So, allegedly, well, it isn't even allegedly. Voyager,
allegedly.
Right. Voyager is currently in the ISM, and while it's there, it got confused. And so while I was reading on everything that's happening with the ISM, I'm really fascinated that this 45-year-old mission is still going strong, and it didn't go into safe mode or have any alerts or anything like that, and which is awesome. But it was just yeah, I'm kind of confused. Can you help me out here? Which is probably due to the high radiation environment that's within the space with going on in the ISM. And again, this is somewhere where no space instrument has ever been before.
Yeah. So do we have a sense of what information NASA was receiving from Voyager? What were they trying to do?
So right now, they're currently investigating that, and they're just basically going with the flow. Whatever happens. Apparently, it takes 2 days for us to receive the mission.
That's crazy. Can you imagine that, trying to debug your spacecraft, and it's a round trip time of 2 days? No, it's 2 days. Yeah,
it gets the data 2 days later, and so this isn't the first time though. This isn't the first time that they had something interesting like this happen. It happened back in 2017 with the thrusters, and so they had to use old thrusters from 37 years prior and put them on. So this isn't the first time that it had issues, but this is definitely interesting.
Yeah, interesting is a way I would describe it. We were talking about this before the show. Voyager is down to 4 watts of power. And how long do you think the Voyagers have left?
That's a really good question. I haven't looked into it yet, but that's something I'll definitely look into. Because the life of Voyager is living a good one right now.
Yeah. Well, so what are they learning from the interstellar medium?
They haven't really, from what I know, they haven't really released anything just yet from this, and particularly because they're still trying to figure everything out.
So and this is the region, we've got where the solar wind, the heliosphere is reaching the collective light, or the collective solar winds from the rest of the stars in the universe, mostly the galaxy, and it's this interaction. So, has Voyager left the solar system yet? Where do you stand on that?
It's in the ISM, so of course it did.
But hasn't crossed the Oort cloud yet, so
Right. It's in that weird place. It's in that in that tricky spot where people like me, my fellow astrochemists, are really, really excited. Yes, more data. So,
well, what kinds of chemistry questions do you have about the interstellar medium?
So, I want to know a little bit. I want to know a little bit more about about its formation and things of that nature, even though we're still studying these things. But like it's complex chemistry. That one is going to be tough. So I really
Right.
want to see what's happening there, because we're still learning more and more about even in the solar system, even like how it helps us understand the solar system even more about our complex chemistry. So we're still learning more about these molecules that are there, and and how they're forming and how they're helping what we know about like protoplanetary disks. So.
Well, I know that researchers, I think from Japan, just in the last couple of weeks, had announced that they'd found the last building blocks for DNA or RNA. RNA. They found the last. So it's like 5 basic building blocks of
DNA.
RNA. Was it
you got it
DNA?
right.
That's right.
It's
Yeah,
DNA.
DNA. So yeah. So there's like 5 basic building blocks that go into DNA, and 3 had already been known, and they were able to turn up the final 2. So it now looks like every single one of the basic building blocks of DNA are all created in space and can be delivered to Earth via various means. And so do you think that those kinds of chemicals could be seen in the interstellar medium streaming off of, say, other stars or
Absolutely.
Yeah.
Absolutely. Yeah. We can definitely, yeah.
And that and well, it's so weird, right? Because like where does the life, where's all the life? Because if all of the building blocks of life have gotten started so early and just out in space, if just like space itself can prepare all the raw ingredients for life, and yet here we are on Earth, and life formed almost instantly as soon as it could. Anyway, I'm completely rabbit holing, but I totally get why this topic
You're
is so
asking for the answer
fascinating.
to the Fermi paradox. Come
It's
on.
bordering on the Fermi paradox. Absolutely. Yeah.
Come on.
Right. And just like every step that goes by, we just find more and more of the precursors of life. We're ready to go out there in the universe, in all the places, all the factories that are producing chemicals. It's kind of stunning. So did NASA say like, don't worry, we got this, or like, don't get too attached to your spacecraft?
Well, they're still looking. They're like, don't worry, but this is very interesting to us. So they're just going with the flow at the moment. They're just going with the flow. So
the spacecraft has lost its telemetry data. We find this interesting. Although the thing that is funny is, like, from what I understand, that the main dish is still pointing back at Earth. Like, they've still got a really good, solid signal with Voyager, even though it has no idea where up and down are.
Exactly. It's very confused.
It's confused, and yet somehow it still knows how to look home, which is great.
Amazing.
Yeah.
It's very much amazing. So like, and it was very cool. Again, it was very cool how it didn't go into safe mode or anything. Right. Like it just didn't like, oh my God. It was just
that's usually like a spacecraft's first move is like, safe mode. But in this case, Voyager just toughed it through. It just goes like, I don't know where I am. I don't know what's going on, but I'm going to tell you all about it. All right. Well, this is I'm prepared emotionally to lose the Voyagers. So, yeah.
You're emotionally prepared.
I'm prepared. I've been prepared for a while. Pam says she is not. She's not prepared.
I mean, I think I'm prepared because it was before my lifetime. So, I mean,
I was there for the launch. Not there. I was on this planet for the launch. So I've been around for the whole thing. All right. Well, it's sad news. We're ready. I'm ready. Pamela's not ready. Kimberly, speaking of spacecraft having problems.
Yeah. Speaking of,
how's Insight doing?
Yeah. Speaking of, don't get attached to your spacecraft. It'd be a shame if something happened to it. So I feel like what we're talking about here. We've known for a little while now that the InSight lander on Mars, this amazing seismology experiment that's been going on Mars since 2018, has been slowly but surely losing power because Mars, of course, is a very dusty place, and InSight gets all of its power from these two solar panels that are on the sides of the lander. And over time, Mars did as Mars does and covered those solar panels with a layer of dust. And that, of course, means that the lander has been taking in much less power. And you can sort of see the difference here in these two images.
Wow.
On the left, when it landed, nice, black, shiny solar panels. And just recently, these...
And gobs of power.
And gobs of power. That's at
Yeah.
about 5,000 watt hours of power per day it started with. And now, with these two solar panels, they're so covered in dust, they almost blend into the surface of Mars. That's how caked these things are. It's only taking in about 400 watts. It's an order of magnitude difference in power. And so, we've known this has been coming because Mars is dusty. Mars tends to do this. We've seen this in the past with Spirit and Opportunity. And with Curiosity, things get covered in dust. And if you're very lucky, Mars will send a dust devil your way and clear off some of that dust. InSight has not been lucky in that regard. They've seen dust devils as close as like 10 meters to the lander.
So close.
Like right there.
Yeah.
But it has not been close enough to clear away enough of the dust from these solar panels to get the power levels back up. The scientists have tried all sorts of very clever tricks to clear off the solar panels. Something that I just when they talked about it at this press conference, they used the arm that's on the lander with the scoop, which is a really clever maneuver where they used the soil of Mars to clear off the soil that's on the solar panels. It seems really counterintuitive, but they scooped up the soil and they very slowly let it upended the scoop over the solar panel, and the dust was carried by the wind and actually scraped off some of the surface layer of dust on the solar panel. It was really clever, and they managed to do that 6 times to extend the power lifetime of the lander. But it's no longer seems to be working, and they don't really have enough power to spare to operate the arm that way anymore. Yeah. So what they've been doing is they've been trying to figure out how long they can stretch the power that they have. The science experiment going for as long as they possibly can to keep collecting data, because it's still collecting data, great data. It just recently measured the strongest Mars quake it has yet detected. It's a magnitude 5. Like, wow, still great science, and they want to keep doing that science for as long as possible. So they've come up with a timeline to sort of stretch this power for as long as they can. They're gonna think they can keep the seismometer running through spring, but then sort of late summer-ish, they're not going to have enough power to run the seismometer anymore. So they're going to turn off SEIS. They're going to technically end their science operations, but they're still going to have just enough power to run the camera, which needs a lot less power than the seismometer. So they're still going to get some pictures throughout the end of the year, and they think probably by the end of the year, there's just not going to be enough power for the lander to operate at all. So, womp womp.
Yeah, womp womp womp.
Yeah.
Now it's funny. Whenever we posted a story about this, and the similar situation is with Ingenuity, that's running out of power as well. We saw Spirit and Opportunity, same thing happened. Really, anything that has with Mars and solar panels, and yet whenever you post, you have these eye-rolling, exasperated, why don't you just, is the beginning of that sentence, and then install a little leaf or
leaf blowers take power.
Leaf blowers take power. Why didn't they just? Why didn't they just? And it is, it's ridiculous.
It's a little bit ridiculous. People, I understand people's urges to be like, why don't you just install, a little brush on your
Yeah,
arm.
a little
to brush
brush, a little windshield
things
wiper, a little
off.
plastic
Yes.
film
Why
that you
didn't
can
you
tear
do
off.
that?
Why don't you just do that? Yeah.
The
They
reason
thought of
is,
that.
yeah, they absolutely did think of that. And the answer is, one, it takes power to do those things. And this is a pretty small lander in terms of, the
Yeah.
types of things that we can put on Mars right now, given our technology. It's a pretty small lander.
Yeah, it's
It was
weight.
a very tight budget for this mission. Keep in mind that I think it was a Discovery class mission. So that's the smallest budget that you can get with NASA. So they were saving every penny that they could. And they really wanted the best seismometer that they could get. That was the primary focus of this mission. They put a great deal of their funding in getting a very sensitive seismometer. They also had two other experiments on there, one of which didn't work, and that was a shame. But when you only have so much money to put together a spacecraft and get it to Mars, you have to prioritize. And so they prioritized, and fairly, I think. They anticipated a 2-year primary mission for InSight. That was about 2 years ago, and so it has doubled its expected lifetime on the surface of Mars, and gotten amazing science doing it. One, it detected Marsquakes, which we did not know existed. So, it discovered this whole new scientific phenomenon.
Yeah.
And I don't think
the most powerful one, it just detected
Yeah,
a magnitude 5.
I don't think that we can understate the fact that this one tiny itty bitty cheap spacecraft launched an entire field of science.
Right.
I want one of
The
those on.
data is being used to literally map the interior of Mars.
Right.
Yeah.
It not only launched a whole new field of Martian seismology, which did not exist 4 years ago. We have the first interior picture of Mars, which we did not have before. We've confirmed that Mars has a liquid iron core. We're getting some hints as to maybe it's not entirely iron nickel, maybe there's some volatiles in there. We've mapped how thick the crust is, how thick the mantle is to really excellent precision. We are getting daily weather updates from the surface of Mars.
Yeah, I love that
We
weather
have a
station.
station on the surface of Mars for the first time, and so we're understanding atmospheric currents and winds. We're understanding sort of the day and night weather cycles going on. There's a magnetic field instrument, so we're getting an understanding of Mars's ancient primordial magnetic field. All of these things are revolutionizing our understanding of Mars's present and its past and its evolution.
Yeah.
And so for a teeny tiny, pretty cheap spacecraft, it really pulled a lot more weight than we ever expected it to. So I think that we can forgive it for not having a windshield wiper.
Can you imagine having one of these on Europa or
one of these on Europa? There's gonna be one on Dragonfly. There's gonna be a seismometer on Dragonfly.
Oh, really?
Going to Titan. Yes.
Yeah.
Don't forget that.
Is there any kind of seismic activity on Titan?
Who knows?
Yeah.
It's a solid surface. It could very well.
It could.
It has no plate tectonics, but then again, neither does Mars.
Yeah.
And there's plenty of
so.
Yeah.
And what about Venus, right? Sure, it would only last for an hour, but an hour of potentially seismic activity, that would be
awesome.
Yeah.
And we've had a seismometer on Venus, but not for a very long time.
And not for a very long time.
And
if nothing else,
nothing goes on Venus for longer than about 30 minutes.
2 hours. 2 hours is the
2
longest.
hours max. Okay. Yeah.
Yeah. We're working on it.
And every lander should have a scoop. InSight has taught us that.
Yes.
Yeah. And
that
helicopter.
arm has been and a helicopter, yeah. But the arm on InSight has been way more useful than initially anticipated. And I think a lot of that is due to how clever the scientific and the technical teams on InSight are to figure out how to use this arm to do all sorts of things it wasn't supposed to do.
Yeah. Fantastic.
Awesome. So
pour one out for InSight next
through the summer.
Yeah.
To keep getting new Marsquake data that's analyzed for years and years to come, of course. But by the end of the year, we may be saying our final toasts to InSight
Yep.
The tiny little mission that could.
Yes.
Thank you, Kimberly.
Yes.
Beth.
Exactly what I call it, Kimberly.
The tiny little mission that could. It's funny. People don't like. I don't think people understand the scale of these different missions, like Kepler versus TESS.
Right.
Right. It
totally
is like
different scale.
It is. Yeah. Exactly. It is a school bus versus a tricycle. I don't know what. I'm trying to think of
Mini
something way
Cooper?
to describe a Mini Cooper, something smaller. Yeah.
Something
yeah.
tiny.
Yeah.
But still
And
technically
so
a car.
Curiosity versus Spirit is like a mama bear and a baby bear.
Yeah,
Like
if
just
you
this.
ever go to like a space history museum and you see the models of Curiosity, like the life-size model of Curiosity versus the
Yeah.
life-size model of Spirit,
Yeah.
and you're like,
Next to
whoa.
the Sojourner, remember the little guy?
Little
Yeah.
guy.
Yeah.
And you just see like it growing in
Platform with
magnitude.
wheels.
Yeah. But yeah, so if you've got ideas for NASA, email them to why didn't you just at nasa.gov.
Yeah.
Beth,
All
you're
right,
gonna raise our spirits now.
Yeah, now that we've talked about things that are not working, let's talk about some science that is working. Scientists have been studying data from the Dawn mission, which was in orbit around Ceres. And we've all seen some of the bright spots that are in it. There's ice in these craters. There's actually a fine mist. It's not, don't call it an atmosphere, but it's a fine mist of ammonia and water that is getting heated up by sunlight and basically sublimating out from the subsurface. And because this particular dwarf planet, former planet, demoted poor asteroids. Anyway, because it actually has ammonia in it, scientists have wondered where it formed, because it's not a very, you don't see a lot of volatiles in the asteroid belt. So these scientists started doing some seriously hardcore computer modeling, crunching planetary formation.
Seriously hard.
Yeah. And I mean, it took them like a decade, it sounds like, to really program all the stuff that they wanted to get in there and basically say, like, let's look at how the solar system formed. And what they found were that there were probably about 3,600 Ceres-like bodies in our solar system that formed out past Saturn, out past the frost line.
Wow.
And because of all of the pushing and shoving and gravitational antics of Jupiter and Saturn, and even the ice giants, and the fact that, you know, a few weeks ago we talked about how we had an ice giant that apparently got yeeted out of our solar system. All of these things basically came together, and Ceres was formed out there and ended up somehow shipped into where the asteroid belt is, and found a nice, happy, stable orbit to exist and not actually get shoved any further.
Thousands of Cereses.
Yes.
And like some were hurled away, some were smashed into the sun, some helped form the moon, some like some are still out there.
Yeah.
That's crazy. So what would have brought Ceres all the way from the Kuiper Belt to the inner solar system?
I'm not sure we could say like that it would be Kuiper Belt. We're talking past Saturn, so you don't want to go too far out. We're talking sort of primordial planetary building blocks.
Okay.
You know, planetesimals in the early solar system. Not everything had been completely scattered, but you know, you had a lot of stuff that kind of clumped together, made these smaller bodies, and you know, because there were so many of them, there were a lot of chances of where they could end up, and Ceres just ended up this far in and found a stable home, which some of the others may have done farther out, but from the looks of it, a lot of them probably just got ejected or pulled into other bodies or broken up into smaller pieces.
That's really interesting. Now you mentioned Dawn, the Dawn mission. That one's doing great though, right?
Yeah, as far as I know.
No, it's dead. It's dead.
No, I know, but it did fine. It's over.
It did fine, but they shut it down. Yeah.
Yeah.
I
got asked today what's the planned end for the Parker Solar Probe, and I thought, I don't want to think about that today. Can we not?
I actually, someone asked a question about that, and I was sort of started to ruminate. Like, would you just keep extending the mission and just take more and more orbits, or would you go deep? Would you get close? Would you push it to the limit?
I mean, I think some of I mean, obviously the fact that they haven't publicly stated, because I did a hunt through stuff, and they haven't publicly stated what the plan is. So I'm sure there's a hope for an extension past 2025.
Yeah, well, the closest plan is 6 million kilometers, and it's at 6.4 million kilometers. So it's almost its operating distance already. So
That's a wild one.
yeah, but by 2025, do you just go, well, let's add more years to the life? Or do you go, let's go closer? How close can we go? I think you know what my answer would be. So, all right, Ashley, we got one more story from you. Leaky helmets, hit us.
All right, we're back to the sad stuff. So apparently there was, I'm going to quit saying apparently because this stuff did happen. So there was...
Allegedly.
Right. So back in March, which we're just now finding out this week. Okay. So work with me here. So there was water in one of the helmets. And so NASA said that this has been a concern for them for quite some time. And so if it were me and I'm out and I'm trying to do some stuff on the International Space Station and I start getting water and stuff like that, nope. I'm telling y'all, bring me back home, send me back home to Earth. I don't care. Like,
we saw this, right? Luca Palmitano several years ago was on a spacewalk and his helmet started to fill up with water.
Exactly. And so
he was not excited about that.
Exactly. And it was like life-threatening. And so what they and
so it happened again.
It happened again. Yep.
This is news to me. I had no idea this has happened. Huh.
Yeah. So right now all of the EMU are like, nope, don't touch them, don't do anything. NASA don't want no. So they're thinking about they're pending an investigation on this issue. And so some of them, because of what happened back in 2013, they do have little packs on, I'm assuming packs on the back of them or whatnot, their helmet absorption packs. And so these can help water come out. And so they'll give you, and it's also like a straw, like breathing tube that's attached so that you can breathe. Because I'm assuming because of this incident.
Okay, so there's like a pad behind them that will absorb the water. Like if water gets into their helmet, there's a place that it can get absorbed. Right. And got a way to breathe so they don't drown in space, which is a thing that astronauts probably were never expecting could happen to them.
Exactly.
Lots of other ways they could die, but drowning
in space.
In space.
Yeah. I'm telling y'all, if it was me, I would have told them, take me home. I don't care. Take me home because drowning? Absolutely not. In space? No.
Yeah.
So right now they're just like, on spacesuits at the moment.
So they're not doing any spacewalks right now while they this problem out?
Correct. Unless it's like life-threatening or any type of emergencies.
So what's the fix?
So they just gonna be bored.
I think they'll have things to do. But what's the fix?
So they're still trying to investigate it at the moment. So it's currently, from what I've seen, it's currently pending investigation.
Wow, that's scary.
Which means we're investigating. We ain't telling y'all.
Yeah. Well, yeah, but I mean, stay inside the station for a little while.
Exactly.
Until they get it out. But it is interesting. I mean, they took from what happened last time in 2013, they took that very seriously, implemented a bunch of changes to the spacesuit to deal with those problems, at least so you don't drown when you're out there. But it sounds like whatever the underlying cause, or maybe there's a new cause that's causing water to leak into the helmets. That's pretty scary.
Right, and that's something that they did see that it was clogging. So they did see, like, that's what the inspection showed, but they still want to understand why is this still happening.
Yeah. Fascinating. All right, well, we've reached the end of our So it's time to let my co-hosts let us know what they're working on. Beth, what are you doing? What's going on, and where can people find out more?
Let's see. I'll be handling a lot of the Study Live duties for the month of June due to the overseas travel of our other host. So expect to see me a lot more over there. In fact, tomorrow I will be talking to Dr. Kelsey Singer about cryovolcanoes on Pluto.
So cool.
You can find SETI Institute on all of your social media, and I am at Planetary Pan pretty much everywhere as well.
You guys are crushing it with the SETI Institute. I gotta say, like, you guys are you're kind of like everywhere, and it's amazing.
Having a
like,
good time, and there's plans. So,
but it's great. It's a really nice mix of science communication and actual science work that's being done, and it's really impressive to sort of watch and see how good a job you guys are doing of getting the word. As a person who is both, I guess, reporting on your news and competing against you in a in a communications stage, yeah, you guys are crushing it. So congratulations on everything you're doing.
Thanks.
Kimberly.
And I wish I was working on something as cool as cryovolcanoes on Pluto. That sounds awesome. I am not working on that, though. I'm talking to a bunch of solar physicists and solar scientists about what we may expect in the upcoming solar maximum and what kind of science they're really excited to do as the sun ramps up its activity in the coming years. So
this could be a good one.
This could be a good one. This is what they're telling me. It could be a good one.
This could be a big cycle. Like, we could see some
and
auroras.
They're like super excited for it. And there's all sorts of excellent science that they're hoping to do to learn about the sun's interior and its surface and what it could do to Earth and Mars and places like that. And eventually, at some point, that will be published on eos.org, where all this stuff is. And I'll probably tweet about it on Twitter at AstroKimCartier, like I do.
Right on. Ashley.
For the next month, I will, for the month of June, I will not only be at the American Astronomical Society Pasadena meeting. This is the first in-person meeting in 2 years.
You're braver than me. I'm not going.
Yeah, my team and I were like, yeah, I want to go. And so, like, apparently, like, a lot of the community members of Black and Astro are going to be, like, in the surrounding area. And then there are some that are coming in, like myself and my vice president and one of my vice presidents. And so, speaking of Black and Astro or Black Space Week, whichever you choose to use, launches Juneteenth until June 25th. And you can find out more at www.blackandastro.com.
Fantastic. I've got a bunch of cool interviews coming tomorrow on my YouTube channel. We've posted them by 8 a.m. I'm talking about space power and photonics. And then I'm going to be talking about the Lunar Crater Radio Telescope later on in the afternoon. And then on Friday, crewed missions to the outer solar system. What would be possible? So yeah, it's going to be a lot of fun. Apart from that, Universe Today and all the things. So come check out all my stuff. All right. Thank you, everyone, for joining us this week. Really appreciate it. Thanks to everyone watching us both on YouTube and on Twitch. Thanks to all the moderators. Thanks to Nancy Graziano for herding all of us cats. We really appreciate it. Thanks to Pamela and the team for engineering this episode. Thanks to all my co-hosts, our special guest. We will see all of you next week. Thanks, everyone.